Alright, we are going to kick off the acids and bases unit by talking about some of their properties. So the words acids, bases probably are fairly familiar to you, but you don't really necessarily know what makes something acidic and what makes something basic and what are the properties of each. So we're going to go over those today, and then we'll go more in depth on acids and bases throughout this unit. So to start off, let's kind of compare and contrast acids and bases. So acids, bases. We'll list some properties of both. We'll see the differences and similarities. So acids, to start off, have a taste that is sour. So yes, you have eaten acids before. You eat them quite a bit, in fact. So anytime you've had a sour candy, that candy has a coating on it. It's usually citric acid that tastes extremely sour, and we actually enjoy that taste as humans. Some other things that are acidic is like vinegar. Vinegar is acidic. Put it in condiments like ketchup to give it that sharp tang that we really enjoy. Bases, on the other hand, taste awful. They have a bitter taste. So we usually think of bases as safer than acids. Acids burn you and kill you, which is not really true. Bases, on the other hand, we think of might be safe because they're the opposite of acids. Also not true. Bases have a very, very bitter taste because most of them are poisonous. So that bitter taste on our tongue is our body telling you, hey, don't eat that, it'll kill you. Acids, on the other hand, largely aren't that dangerous. If you've ever kind of burped and some stuff came up into your back of your throat and it tasted really sour and tingly, that's because your stomach is full of hydrochloric acid and you just belched up a little bit of it. So, I mean, we've got acid all over in our stomach. Eating a little bit isn't going to do any damage. Bases have that very, very bitter taste. Think of a bar of soap. If you've ever said a naughty word and your mother shoved a bar of soap in your mouth, it tasted bitter because soap is a base. And that brings us to the next thing, what they're typically used in. So acids are typically used in foods. They're used in other things. Batteries a lot of times will use acids. But foods is a very, very common source for acids. Vinegar, soda pop. If you look on the back of a jug of soda pop, it usually says something like phosphoric acid. And that's because it gives it kind of that sting, that tingle that we enjoy. Colas use a large amount of phosphoric acid for that reason. Bases, on the other hand, are cleaning products. Okay, we don't typically eat cleaning products because they're poisonous, and that's because they're basic. So cleaners, bleach, ammonia, Windex, soap, shampoo, all of those types of things are bases. That's why they taste bitter, because they're so bad for us. The next property would be the pH scale. So the pH scale is a measurement that we use to figure out whether something's acidic or basic, and then how acidic or how basic. It's a lowercase p and a capital H right there on both of those. So on the pH scale, acids will range from 0 to 7. Bases, on the other hand, will range from 7 to 14. To note, though, acids are not at 7 and bases are not at 7. So 7 is actually neutral. That's right in the middle, neither acidic nor basic. So like pure water would be 7. Anything below 7 would be acidic. Anything above 7 would be basic. And the scale actually does go below 0 and it does go above 14. But when you see it written on a piece of paper, just for convention's sake, we range it from 0 to 14. 7 being the dead center, and that would be the neutral compounds. And then the last property we're going to look at is litmus paper. So here's a little image that shows litmus paper. There is 2 different types of litmus paper. There's red litmus paper. So this right here, if you look at this half, that would be the untested half. So that's red litmus paper. This is blue litmus paper. If you have red litmus paper and you put a base on it, it will turn the paper blue. So bases turn litmus paper blue, whereas if you have some blue litmus paper, and we can see right here on the side of the paper, that's what blue litmus paper looks like. It's kind of a purplish color, really. And if you put an acid on blue litmus paper, it will turn it red. So bases turn litmus blue, acids turn litmus red. What happens if you put an acid on red litmus paper? Well, it turns it red, but it's already red, so you don't see anything. And if you put a base on blue litmus paper, it turns it blue, but it's already blue, so you don't see anything. So we can use litmus paper to test if something's acidic or basic, and it's just based upon those two different papers. So if you put something on blue and it turns red, it's acidic. If you put it on red and it turns it blue, it's basic. If you put it on red and it stays red, then it's acidic. If you put it on blue and it stays blue, then it's basic. Now let's talk about some of the terms that go along with acids and bases. I'm going to throw a lot of formulas and concepts and definitions here at you. Write these down somewhere and circle them, because that way if you're ever listening to a video in the future, or you're sitting in class and, I don't remember what that means, you can flip back to it and look it up real quick. There's going to be a lot of different things that we're going to use a lot during this class, and until you get used to the vocab, it'll be good to have access to those. So the first thing that we're going to look at is H+. So H+, you're going to hear me I'll call H+ sometimes, but I'll also refer to it as a proton. So what it is it's a positively charged hydrogen atom. And if we think of what hydrogen is, hydrogen on the periodic table would be one proton and one electron floating around in the electron cloud. If something is positive, that means it's a cation, which means it has lost an electron. So if we take this hydrogen and we lose its electron, all that we have left is a single proton, because there is no neutrons inside of a hydrogen atom. And so really an H+, a hydrogen cation, is nothing more than a single proton by itself. So H+ is also called a proton, and that is a big part of the acid-base chemistry. That's actually where the H comes from in pH. Alright, the other thing you're going to see a lot of is H3O+. H3O+ is referred to as a hydronium ion. If you look on your common ion sheet, it's actually on there. So a hydronium ion, H3O+, and really these two things are the exact same. Alright, H+ and H3O+, going to refer to them interchangeably. They both indicate an acid. So anytime you have an acidic solution, you have a high amount of H+ or H3O+, and really they're the exact same thing. All acids and base solutions are liquids. They all take place in water. They're all aqueous. And so if we think about water, which is H2O, and protons, which are H+, those H+ dudes, they don't like just hanging out by themselves. That positive charge, it's too much for them. So what they're going to do is they'll find something to stick to, and what they stick to is water. And so all H+ really are not H+, they're not just protons by themselves. They latch themselves onto a water, which makes H3O+. So this right here is really just a shorthand for that right there. Those two things, though, write this down in your brains, are the exact same thing. H+, H3O+. They indicate an abundance of hydrogen protons in the water. In this case, they're attached to the water molecules. In this case, we're ignoring the water molecules. But they mean the same thing, and they both indicate an acid. Here's an example of what I mean. If we look at hydrochloric acid, which is HCl, there's two different ways we can think of hydrochloric acid and what makes it an acid. So if we put HCl in water, it ionizes, so it's AQ, which means it breaks apart into H+ and Cl-. So remember, something that's put in a solution that's aqueous breaks apart, it ionizes into its individual ions. And what HCl it breaks apart into is H+ and Cl-. So this guy right here, that H+, that is why hydrochloric acid is an acid, because it generates those H+ in the water. Another way we can write this exact same thing is HCl. Okay, it ionizes when we put it in water, so let's say HCl plus H2O. When it does that, this little hydrogen right there, it's not going to just break off by itself. It'll actually latch itself onto the water. So what we end up producing is H3O plus Cl-. And this guy right here, the hydronium, that's what makes hydrochloric acid an acid. So these two equations are the exact same thing. This one's in water. We're just ignoring the water as a spectator ion. This one, we wrote the water in and wrote it as hydronium. But both of them show hydrochloric acid as an acid because it produces protons and or hydroniums in the water. And next is something probably a little bit more familiar, and that is hydroxide, OH-. OH- is what makes things basic. So all bases have hydroxides in them. We've seen lots of hydroxides. We use them a lot. Sodium hydroxide, magnesium hydroxide. All of those are really bases. We don't refer to, like HCl as hydrochloric acid. We don't say sodium hydroxide base. But you do recognize things that are basic because they have that hydroxide in them. Anytime you see an OH, almost always it's going to be a base. So an example of that would just be sodium hydroxide. So sodium hydroxide, when we put it into water, it breaks apart into Na plus and OH minus. And this guy right here, the OH minus, is why sodium hydroxide is a base, because it generates those OH minuses. There is no other term, so it doesn't latch onto water or any such thing. It's just hydroxides. And the last term for our acids and bases beginning is the brackets. Okay, so little square brackets like that. Probably should have introduced this during solutions because it applies to there as well. But you are going to see it a lot in acids and bases. So anytime you see a little square bracket and there's going to be some kind of formula inside, we'll just say X for now. So fill in the blank. Something will be inside those brackets. What that means is the concentration of, in this case, X in molarity. And molarity is moles per liter. So, for example, if you were to see HCl in brackets is equal to 0.1 m, that means you have a concentration of HCl of 0.1 m. So instead of me saying you have a solution of hydrochloric acid with a 0.1 molar concentration, you would just see this right here. HCl in brackets equals 0.1. And you can do the same thing with bases, so NaOH is equal to, throw out a number, 1.2 molar. Just means we have a 1.2 molar solution of sodium hydroxide. Alright, so that's it for all the new terms and some of the ideas of what makes something acidic and basic, or what kind of things are acids and bases. Hopefully you guys took good notes on this that you can refer back to later, because there's going to be a lot of new information coming at you real fast.